going to be doing some step 1 integrals today. So yeah, let's dive straight into it. So let's call our first integral I. And I is the integral from 0 to pi over 4 of tan to the n of x sec squared x dx. Now, you might have multiple ideas here. You might be thinking, how do I link tan and sec? I do know that tan x differentiates to sec squared x. Could I use that to my advantage? Well, I definitely can. If I let u equal tan to the n x, that means u dash is equal to n tan to the n minus 1 x sec squared x by the chain rule. V dash equal to sec squared x. So I'm going to do integration by parts here. And my v is tan x. I can rewrite this integral as my u times my v. So I'm gonna have u times v 0 to pi over 4 minus the integral of my v du. So I'm gonna have n tan n minus 1 x sec squared x multiplied by tan x dx from 0 to pi over 4. And hopefully what you can notice here, so this is going to be tan to the n plus 1 x from 0 to pi over 4 minus n lots of the integral from 0 to pi over 4 of these multiply to just give me a tan to the n x sec squared x dx. But this is exactly equal to I. So I can say this is I equals to tan n plus 1 pi over 4 minus tan n plus 1 0 minus n I, which implies I lots of n plus 1 equals, if I add ni to both sides. Now, tan of pi over 4 is simply 1, and 1 raised to any power, right, is just going to be 1. So I'm going to have 1, and tan of 0 is 0, and likewise 0 raised to any power is 0. So I'm going to have minus 0 here, which is just 1. Therefore, I equals 1 over n plus 1. And that is our first part. Okay, our second part's a little bit more tricky, but it's a very similar idea. So we're going to have the integral from 0 to pi over 4 of sec to the n x tan x dx. Now, let's have a think about why the integration by parts here actually worked, because this is the key to solving this problem. Well, it's because tan x differentiates to sec squared x. But right now I have a sec x. Now sec x doesn't differentiate to tan x, but sec x differentiates to sec x tan x. So what I can do is I can rewrite this integral as sec to the n minus 1 x times sec x tan x. And now I can use a similar method to try and integrate this. So I'm going to make u equal to my sec to the n minus 1 x. That means my u dash by the chain rule is going to be n minus 1 sec to the power n minus 2 x multiplied by the derivative of the inside function, which is sec x. So we're going to multiply that by sec x tan x Simplifying this is going to give us n minus 1 lots of sec to the n minus 1, sorry, x tan x. We're going to make v dash equal to sec x tan x, so that our v is equal to sec x. And now we can rewrite this integral as our u times our v. So our u is going to be sec to the n minus 1. X times our v, which is just sec x, from 0 to pi over 4, minus the integral of v du. So n minus 1 lots of sec to the n minus 1 x tan x. Multiply that by sec x dx, and our bounds don't change. So we're going to have here sec to the n x evaluated from 0 to pi over 4 minus, now this looks very similar to our original integral I, right? So if I bring that n minus 1 out, and then I multiply sec to the n minus 1 x multiplied by sec x, I'm going to have sec to the n x tan x dx, which is our I. So I'm going to add n minus 1 lots of I to the other side. So I'm going to have I lots of 1 plus n minus 1 equals. Now, let's have a think here. Sec to the n x, well, sec x is 1 over cos x, right? So I'm going to have 1 over cos to the n lots of pi over 4 minus 1 over cos to the n lots of cos to the n of 0. Okay? And so if I have here cos of pi over 4 is 1 over root 2. So I'm going to have 1 over root 2 to the n minus 1 over, now cos of 0 is simply 1, and 1 to the n is just 1. And so this is going to give me root 2 to the power of n minus 1. And here on the left-hand side, I'm just going to be left with n lots of I. So that implies I is equal to root 2 to the power of n minus 1 all over n. Okay, and that is how you do these two integrals. Hope you guys enjoyed it. Let me know how you found it in the comments.